for coming. This is joint work with Jonathan Shi and David Storer, who are in the audience. I'm Tony Ma from Princeton. I'm going to talk about over-complete tensor decomposition using sum of squares algorithms. All right, so let me start by defining the problem. So we are given a tensor T of the following form. So T is the summation of rank 1 tensor, AI, tensor, AI, tensor, AI. Each of these AI lives in D dimension, and so the overall tensor is in D times D dimension. So we are given the entries of this tensor, and our goal is to find A1 up to AN. This is often called over-complete tensor decomposition if N is larger than D, and this is often the most challenging case. For downstream applications, it's often useful to think about the situations when you have a noise tensor added to T, and this noise often comes from sampling error in the machine learning applications. We are going to talk about noise tolerance, although let me mention that this problem is already challenging even without the noise. Actually, it is NP hard in the worst case, so that's why we have to work with average case problem, as you will see. So the motivation here is that this is tensor decomposition algorithm is kind of the key algorithmic tool for many unsupervised learning problems. I have a long list of unsupervised learning problems here, and actually this is just a subsampling of many of these works in this line of research. And I guess what is more important is that still there are many open questions in unsupervised learning unsupervised learning which could be solved if you have better algorithmic tools for tensor decomposition. So for example, the last one here is an example. In our recent work, we used the machinery developed in the paper of this talk and with other techniques to solve some unsupervised learning problems, namely Bayesian night, that we couldn't do before. All right, so in this talk, we are going to focus on random over-complete 3-order tensor. So A1 up to N are assumed to be uniformly drawn from the unit sphere. We could handle pretty large over-completeness, so N could be as large as D to the 3/2. And the noise tolerance here is that the noise tensor E, viewed as a D squared by D matrix, has spectral norm less than negative 1. And the theorem that we're going to prove is that with high probability over the randomness of AIs, we have a sum of squares algorithm that finds all of the components up to error 0.1 in polynomial time. So the error here can be boosted to the optimal level using either local search algorithm or another sum of squares algorithm, which is a little bit more complicated. So although in this talk we're only going to focus on 0.1 error. So in this paper we have several other results, and let me compare them with prior works. So the simplest setting for tensor decomposition is this low rank case, when the rank N is less than the dimension D. So Su and Kakate considered the orthogonal case, and Jenrich and Goyo et al. Considers the linearly independent case. Our results will imply a fast and more robust algorithm for the orthogonal case. It turns out for higher order tensor, the problem becomes slightly easier. So Bahaskara et al. Had a polynomial time algorithm for 5th order tensor over complete 5th order tensor under smooth analysis framework. And our results give an algorithm for the 4th order tensor, which is slightly more preferable because in applications people want the lower order tensor for both sample complexity and runtime. Barak et al. Had a quasi-polynomial time algorithm for 1 over epsilon order tensor under nearly isotropic assumptions on AIs, and we improve it to polynomial time. Finally, regarding the random 3-order tensor that I have defined for you, Rongo and myself had a quasi-polynomial time algorithm for N is at most D to the 3/2. Hopkins et al. Had a fast polynomial time algorithm for N is at most D to the 4/3. And in this talk, we are going to have a polynomial time algorithm for N is at most D to the 3/2. And because we are using sum of squares algorithms, it automatically handle a pretty large amount of noise. All right. So we are going to use sum of squares algorithm. So I guess in the previous talk, Sam defined it as a Superman. So now let me have a little bit more concrete introduction. So let's consider we have a polynomial program, right? A system of polynomial equations, and we want to find a feasible solution for it. Let's have a very wishful thinking scenario, right? Suppose somebody give you a distribution D supporting feasible solutions. Then it's almost done because you can just draw one sample from it. Or equivalently, if somebody gives you the expectation operator defined over this distribution D, then it's kind of equivalent to having the distribution D. So I guess the best way to think about this expectation operator is just if you plug in any monomials into it, it will return you the moments of D. And from the moments, you can recover distribution. So we didn't do anything here because this is pretty much the same problem as we want to solve before. So we couldn't hope to have such a general thing. So what sum of squares algorithm can do for you is that it will give you a pseudo expectation that behaves like an actual expectation on low degree sum of square polynomials. And just clarify the notation here. This E tilde is a linear operator that maps polynomial with degree D less than k to a real number R, and it behaves like an actual expectation on low degree sum of squares if you plug in low degree sum of square polynomials into it. This is pretty much what you need to know about sum of squares for this talk. So let's see how do we use it for our problem. So we have to start with a polynomial program and then do the relaxation. So let's see what polynomial program we want to write. So let's consider this function f of x, which is the multilinear form defined over the tensor T. And because the tensor is a low rank tensor, you can write this multilinear form in the way that it's a summation of ai.x cubed. And our polynomial program will be just, first we enforce f of x is larger than 1 minus epsilon, and secondly, we have this normalization constraint, norm of x is 1. It turns out that this suffices if you can solve this polynomial program, because all the feasible solutions, any feasible solution is close to one of the AIs. So basically, the set of feasible solutions are just the neighborhood around this AIs that we want to recover. So now let's do the relaxation. Let's do the wishful thinking again. So ideally, we want to have an expectation operator for distribution D supported approximately on all of these AIs. So that's the ideal case. What sum of squares algorithm can do for you is that it will give you a pseudo expectation that behaves like this real expectation on low degree polynomials. And our rounding have to recover these AIs from the pseudo expectation. How do we do this? There's this very nice paradigm for designing rounding algorithms for pseudo expectation. So basically, the idea is that let's assume the ideal case first, because that's something that we have to solve if you want to solve the case when you are given this weaker pseudo expectation. Let's just elaborate on this. So in this ideal case, we have this kind of necessary thought experiment. So let's assume that we have actual distribution supported on the feasible solutions. And then let's design an algorithm that only have access to the low degree moments of distribution D. And then let's prove the algorithm works. Suppose we have done with this, then this is the real algorithm analysis. So the real algorithm is that we first obtain the pseudo expectation using a sum of squares algorithm, basically semi-definite programming. And then we replace every occurrence of the moments on the left-hand side by pseudo expectation. And then the real analysis will be that if we can replace the analysis on the left-hand side by a sum of squares proof, then we are done. So the rationale here behind it is that pseudo expectation behaves like real expectation on low degree polynomials, and therefore sum of squares proofs can't distinguish the case on the left-hand side and the case on the right-hand side. And therefore, if it works for the left-hand side, it should also work for the right-hand side. All right, so kind of the beauty of this paradigm is that it kind of divided this kind of complicated project into kind of two parts. Right? The first thing to do is we have to do this thought experiment, which contains probably most of the innovative things about designing the algorithm. And then the next thing to do is the sum of squares proof, which is could be pretty complicated, pretty technical, but you have some guidance because you have already got a real proof, and you just want to translate it into an alternative proof, which could be complicated, but it's relatively slightly easier, I guess. Okay, so I guess this is also a good excuse to just to show a proof sketch for the thought experiment. Right. Okay, so here is the thought experiment for our problem. So we have said that the feasible solutions is basically any feasible solution is close to one of these AIs, and let's just assume that we have a real distribution support uniformly over A1 height up to AN height, and this AI height are close to AI. And we have access to low-degree moments of the distribution. And we want to design an algorithm that gets A1 up to A and back. So if you think about it for a minute, then you only have access to the low-degree moments, then maybe the most naive thing to do, the straightforward thing to do, is to look at what the moment is. And let's look at the third-order moment, right? Because this is just a uniform distribution over this AI hat, you can compute the third-order moment easily. It's 1 over n times the sum of AI hat to the tensor power 3. So this is pretty much the tensor decomposition problem again. It's kind of the same problem. And we didn't really gain anything from all of this, even in this thought experiment. However, the key is that if you consider higher order moments, let's say we take 6th order moment, and similarly we can compute it and get this average of AI hat to the tensor power 6. And now, so first of all, the amazing thing here is that sum of squares allows you de facto access to the 6th order tensor, even though you only have access to the 3rd order tensor to begin with. And secondly, the problem becomes easier because now if you, let's say, define bi hat to be ai hat to the tensor power 2, this bi hat lives in d square dimension, and this M6, right, is just a 3rd order tensor over bi hat. And the crucial thing is that it's bi hat, because the dimension is d square, you can expect them to be approximately orthogonal when n is less than d squared. While those AIs couldn't be approximately orthogonal because they are n vectors and n is larger than d, then they are not even linearly independent. So in some sense, what we have said is that there's a reduction from the over complete random tensor decomposition within sum of squares to approximately orthogonal tensor decomposition, and which sounds like an easier problem. So here, this orthogonal is our friend because we know how to solve the orthogonal case. The approximation is the kind of the issue that we are going to address in the next 2 slides. Right. So the issue here is that this bi hat is just ai hat to the tensor power 2, which is only close to ai to the tensor power 2. And we don't really have too much control on the error. And so we have to solve this approximated orthogonal tensor problem. So given this reduction, it makes sense to just demonstrate this idea on the orthogonal case in the next 2 slides. So for the next 2 slides, we are just going to assume that AI is orthogonal, and AI hat are approximately orthogonal because they are close to AI. Right. So in the next 2 slides, we are only going to do the orthogonal case. So for the orthogonal case, there was this generate algorithm, and we need a robust version because we want to deal with the noise. So let's start with this 3rd order tensor. We have this sum of ai hat to the tensor power 3. And let's do this random contraction. So basically what I mean is that let's take a Gaussian vector G from the spherical Gaussian. Let's consider this M of G dot dot. This is basically, you consider M as a multilinear form, and you plug in G into one of the modes. If that notation sounds not familiar to you, then basically what I mean is just this expectation of this weighted kind of covariance matrix. So this object, right, because again D is a discrete distribution, uniform distribution over ai hat, we can compute this expectation. We get this weighted, sum over ai hat transpose. So here is a simple lemma. So basically, with 1 over n, inverse Pauli probability, this expectation of this matrix has this form. So basically, the first term in this sum is the dominating term, and all the rest have spectrum norm much smaller than the first term. And suppose this event happens, then we're done, because A1 hat is approximately the top eigenvector. However, so this is kind of simple. I'm going to omit the proof. However, there's a caveat here, because this is not really true, and I was cheating. So what is really true is that you require the sum of ai hat transpose to be less than 1. And we shouldn't take this for granted, because ai is orthogonal doesn't mean that ai hat are orthogonal. The reason is that all these arrows could accumulate in the same direction, and so that they are as large as n to the epsilon. So this is kind of like a worst case scenario when you have all these orthogonal vectors, and you'll perturb all of them with the same direction, these red arrows, and the spectral norm of the AI hat are no longer bounded by any constant. All right. So, okay, so the idea to fix this is that we want to add constraints that enforce this AI hat to be isotropic. So let me have a small warning here. So this AI hat are those kind of feasible solutions, that in our thought experiment, and we are not allowed to really add constraints on them. We are only allowed to add constraints on the moments of this distribution D. But the good news here is that the sum of like 1 over n times sum of AI hat transpose, this is exactly the two moments of this distribution D that we are considering. So basically, this suggests that we can add this additional constraint on this distribution D. So we require that the expectation of the covariance, basically the covariance matrix of this distribution, to have spectral norm less than 1 over n. So let's just do some sanity check. First of all, this is a convex constraint because the norm of anything less than anything is a convex constraint. And secondly, this is a feasible constraint because uniform distribution over the AIs, the desired solution, satisfies this exactly because AIs are orthogonal. And the kind of the intuition behind it is that before we have this kind of worst case situation, very worst case situation, and now with this new constraint, you enforce all of this AI hat to have error, to have an error that can be that's spread out. So basically here is the lemma, the real lemma that we are going to prove. But suppose we have an actual distribution, supported on these feasible solutions, and it satisfies in addition this constraint. Then with inverse Pauli probability, the top eigenvector of this matrix is 1-to-1 close to A1 hat. And you can repeat this many times to get all of the other AI hat. And if you get AI hat, you get approximate out of AI. So just to briefly mention what you do when you are not in a thought experiment, when you do this, the real algorithm. Then what you do is that in a real algorithm, you augment this sum of squares relaxation by this additional constraint on the second moment of basically the degree 2 pseudo moment. So we just require that the pseudo expectation operator to satisfy that the spectral norm of this matrix to be less than 1 over n. All right. So I guess what we have done is basically this thought experiment, a proof sketch for the thought experiment, and the remaining thing that we didn't show is how to make this proof a sum of squares proof. All right, just to wrap up. So we have this polynomial time algorithm for random third order over complete tensor with n is at most d to the 3 halves, and noise tolerance is lid of 1 noise tolerance in spectral norm. And we have some other results that improve BKS to polynomial time, and we have a robust fourth order tensor and a smooth analysis. So I guess the major open question is that how to have a robust third order tensor decomposition and a smooth analysis. And another one is that whether we can speed up the current sum of squares algorithm to make it more practical. That's it. Thanks.
We have a little bit of time for questions. Can thank the speaker again.